Welcome to calculus. Can we evaluate this integral? At first glance, this integral appears formidable. The combination of a squared logarithm inside an oscillatory sine function, an infinite domain, and the denominator factor 1 plus x makes standard techniques fail. Instead of attacking this integral directly, we are going to transform it into a much simpler oscillatory integral. The presence of the logarithm in the integrand strongly suggests a natural logarithmic substitution. Let t equal the natural logarithm of x. Then x becomes e to the t, and the differential dx becomes e to the t dt. Now examine the integration bounds. As x approaches 0 from the right, t tends to negative infinity. As x approaches infinity, t tends to positive infinity. Thus, the domain spans the entire real line. Substituting these pieces transforms our original integral into the integral from negative infinity to positive infinity of sine of 2t squared over t squared, times e to the t over 1 plus e to the t, dt. Now comes the crucial trick. Notice that the oscillatory term depends solely on t squared, making h of t an even function that is perfectly symmetric under negation. Meanwhile, look at the weight factor g of t. Evaluating g at minus t gives 1 over e to the t plus 1. Therefore, g of t plus g of minus t sums identically to 1. Now we split the real line integral into positive and negative intervals. Substituting t with minus t in the second integral reverses the limits from 0 to infinity, while h of minus t remains unchanged. Factoring out h of t combines the weights into g of t plus g of minus t, which collapses directly to 1. The entire complicated algebraic denominator 1 plus x has completely vanished. We are left with a classic oscillatory integral. Now, let us apply integration by parts. We choose u equals sine of 2t squared, and dv equals dt over t squared. Differentiating gives du equals 4t cosine of 2t squared dt, and integrating dv gives v equals minus 1 over t. Applying the integration by parts formula gives the boundary evaluation plus 4 times the integral of cosine of 2t squared dt. As t approaches infinity, sine is bounded while denominator grows without bound, so the upper limit is 0. As t approaches 0, sine of 2t squared is asymptotically 2t squared, which divided by t also vanishes to 0. Thus, the boundary term vanishes completely, leaving 4 times the integral of cosine of 2t squared dt. This is a classic Fresnel oscillatory integral. Recall the Fresnel integral identity. The integral of cosine of a t squared evaluates to 1 over 2 times the square root of pi over 2a. For a equals 2, this evaluates to square root of 2 pi over 4. Multiplying by the factor of 4 neatly cancels the denominator, leaving the square root of 2 pi. And that is our exact result. A complicated-looking integral over the entire positive real axis reduces, through logarithmic substitution and symmetry, to the simple answer, square root of 2 pi. For getting more videos like this, please subscribe to our channel Calculus.